Hello guys, welcome to our YouTube channel. Today we will discuss about the different types of phases in steels. So in this video we will see few phases available in the steels. So we will also discuss about the few phases which is available in iron carbon diagram and few phases which are available in CCT diagram. So there are two kinds of phases. First is equilibrium phases and second is non-equilibrium phases. For the non-equilibrium phases, we will see like Austenite, sorbite, benite and martensite. And for the equilibrium phases, which we'll see under the iron carbon phase diagram, that is ferrite, austenite, cementite, perlite and lead-aburite. So this is our iron carbon phase diagram. In this iron carbon phase diagram, there are basically 5 phases available. First, ferrite, second austenite, third cementite, fourth perlite and lead-aburite. So these are the 5 phases available. In case of ferrite, we have two, alpha ferrite and delta ferrite, with the same kind of structure, that is BCC, but difference in temperature. So this alpha ferrite is this one and this delta ferrite is this one. So one is forming near around this range and delta ferrite forms in this range. And this austenite, this gamma austenite having FCC structure, and it forms in this range. This is the temperature range. For the cementite, this forms up to this range. So this is the common presence of cementite in the iron carbon phase diagram. Perlite, this forms when gamma transforms to alpha plus Fe3C. So at the temperature of 723 degrees centigrade, this is called invariant reaction. This is the invariant point. So here perlite forms. And lead-aburite, this forms during the eutectic reaction. So the eutectic reaction occurs at this point when liquid changes to solid. So here this temperature is 1147 or 1143 degree centigrade temperature, and this is the eutectic point. Invariant reaction occurs in this region. So upon cooling at 1147 degree centigrade temperature, here liquid changes to gamma plus Fe3C, where 100% lead-aburite formation is this. And here on the eutectide reaction, when gamma transforms to alpha plus Fe3C, 100% perlite forms. So this is the perlite reaction. This is the eutectide reaction which forms the perlite, and this is the eutectic reaction which forms the lead-aburite. Now we will discuss all the phases one by one. So first, the ferrite. So I have already told in the previous slide that ferrite has two types, alpha and delta. Both are different with the temperature range having the same BCC structure. So the BCC structure is of like this. So there will be one atom, both are the same. So this is kind of BCC structure. So ferrite is an interstitial solid solution of a small amount of carbon dissolved in BCC crystal structure, and the maximum solubility of carbon is 0.025% at 723 degrees centigrade temperature, and at a room temperature the solubility is around 0.008% only. And ferrite is soft, ductile and is of low strength among all phases of iron carbon alloys. So in this slide the key points are like we need to know about to remember like what is the maximum solubility of carbon in iron at what temperature. Like this is at the room temperature and this is the 723 degrees centigrade temperature. So this is the, like multiple choice questions can be asked in many exams. So this need to remember. And also this is the alpha ferrite or delta ferrite. So the temperature range difference should also be remember. So this fact is about alpha ferrite. And for delta ferrite, the solubility of carbon, that percentage of carbon is 0.098% at the temperature of 1493 degrees centigrade. So these are the different solubilities because solubility depends on the temperature. Now we will see the second phase, that is austenite. So austenite is an interstitial solid solution of carbon up to 2% at a temperature of 1147 degrees centigrade, and it is in FCC crystal structure. So the crystal structure is FCC like. They have only face center atoms. The outer one. So this is the FCC crystal structure, and it is normally unstable at room temperature, and the behavior of austenite is non-magnetic. So in case of austenite, as we have seen that it is stable in the temperature range of 912 to 1394 degrees centigrade. So this is the stability range of austenite. It is called gamma iron having FCC structure. And one question comes like where the carbon goes. So carbon, that is the location of 0 0 half, that is the edge centers and face center, that is half half half, which includes the body center. This is the edge center. The size of the largest atom that can fit in this void is 0.52 angstrom, as the solubility is larger here as compared to ferrite. So the maximum solubility is at 1146 degrees centigrade, is around 2.18% or 9.1 atom percent. So here the carbon goes at the octahedral site because they are having the bigger voids than the tetrahedral. One more fact, that the solubility of carbon in iron here in austenite is more than ferrite, because here the carbon size, which is this for carbon atom size, and the largest atom that can fit into the void is 0.52 angstrom. So there is no much difference in the size, so there will be the solubility is larger. Solubility for austenite will be larger than solubility of carbon in case of ferrite. Next, cementite. So when carbon in iron exceeds the solubility limit, it forms a secondary phase which is commonly known as cementite, that is Fe3C. This is also called iron carbide, which is Fe3C. It contains up to 6.67% carbon by weight and has a orthorhombic crystal structure. Has a complex orthorhombic crystal structure where with 12 iron atoms and 4 carbon atoms in the unit cell. And one more fact, it is a typical compound of low tensile strength but high compressive strength and ferromagnetic in nature. It is the hardest structure in iron carbide system. Fe3C has 6.67% of carbon by weight. So we have already discussed about this in our previous video, so you can watch there. So why this iron In iron carbon phase diagram, there is a cementite phase which is a 6.67 weight percent of carbon. We have already proven this fact in our previous video. You can watch. Next phase is Ferrite. So the mechanical mixture of ferrite and cementite formed at 727 degrees centigrade, which is called eutectide reaction on a very slow cooling, is known as Ferrite, and it consists of alternate layers of ferrite and cementite, like this. Alternate layers. There will be some difference, like so it is a product of eutectide transformation at 727 degrees centigrade temperature and a composition of around 0.77% of carbon. And perlite is fairly soft and its hardness lies between that of the ferrite and cementite. It appears like a fingerprint in structure, like I told the morphology, which is lamellar. It's called lamellae. Next one is ledaverite. It forms as a reaction of eutectic transformation. So ledaverite is a eutectic lamellar mixture of austenite and cementite. It contains 6.67% of carbon and is formed at 1147 degrees centigrade by eutectic reaction. Further, ledaverite is unstable and transforms into ferrite and cementite at 726 degree centigrade. So another fact is cementite is hard, as we have seen in the previous slide, but brittle, and perlite is also fairly hard, and this is that alpha plus Fe3C. So alpha gives the toughness and this is the hardness, cementite. Therefore the transformed ledaverite is also hard and brittle. Next is benite. So benite is an isothermal transformation product and is produced on isothermal transformation at temperature between 550 degrees centigrade and 240 degrees centigrade. It consists of an aggregate of ferrite and cementite once again, but this is a non-lamellar. The difference between benite and perlite. So when austenite is cooled rapidly past the nose of the C curve, so this is the transformation temperature versus time. So this is the C curve. So it is kept isothermally in a constant temperature bath and it transformed to an extremely fine non-lamellar mixture, which is of ferrite and cementite, that is known as benite. And several descriptions of benite are in use, but the subject is complicated by experimental difficulties, the lack of general agreement. We will follow the classical definition, which divides benite into two parts, that is upper benite and lower benite. Upper benite forms between 550 and 350 degrees centigrade temperature. So this is a 550 to this 350. This is the upper benitic range, which is here, and the lower benite also forms in the range of below 350. So lower benite below 350, and for the upper benite 550 to 350 degrees centigrade temperature. So if both upper and lower benite, the ferrite units grow by rejection the excess carbon into the surrounding regions, where the carbide eventually nucleates in order to give the benitic transformation. So the upper benite has a structure of Phe3 and lower benite acicular. So there is also one more difference in the hardness of upper benite and lower benite. So upper benite has a hardness of around 40 to 50 HRC, and the acicular one, which is the lower benite, has a hardness of around 50 to 55 HRC due to the fine nature, and this is due to the coarse nature. Next phase is martensite. So it is a supersaturated solid solution of carbon in iron. So martensite is formed by transformation of austenite below the MS temperature. So this is the MS temperature, martensitic start temperature, and it is an supersaturated solid solution of carbon in alpha iron and has a BCC or BCT both lattice structure, and it's as a product of quenching. So if we escape this nose, if we are starting from here and we are cooling like this, we are escaping this nose, so this will form the martensite. And in this one, the BCC or BCT lattice structure will depend on the C by A ratio, like 2 FCC interpenetrating FCC gives the martensitic structure like this one. So sometimes it would be BCT or sometimes it would be BCC, that will depend on the C by A ratio. And the martensite finish temperature is MF. And in the iron carbon diagram, this is one of the hardest phase due to the rapid quenching. Sorry, in case of CCT or TTT, not in iron carbon, this is one of the hardest phase due to the rapid quenching. So in the final phases observed in CCT or TTT diagram of steels, we will see the Austenite and Sorbite. Now we will see the difference between these two. So cooling of Austenite in a furnace yields coarse perlite, while air cooling gives fine perlite of hardness of 20 to 25 HRC. So extremely fine perlite near the nose of the C curve called Austenite, and air cooled fine perlite is called Sorbite. So what is the difference between these two technically? So both are having lamellar morphology of alpha and cementite, so with the difference of interlamellar spacing. So this Sorbite having the less interlamellar spacing than Austenite, as it forms earlier, and this Sorbite forms later on. So this is the basic difference between Austenite and Sorbite. In the CCT or DTT diagram, earlier we used these Austenite and Sorbite names in case of according to the cooling rate, but now generally we use this coarse perlite, fine perlite, and very fine perlite. These three are generally in the practice now. Thank you. So once again, thank you very much for watching this video, and please share, like, subscribe, and refer to your friends, colleagues this metallurgical engineering channel. And please comment if you would like to suggest us any topic. We will make sure that we will present those topics also. Thank you.